Earth if you wait long enough. So, of course, being in Norway, and then one of the things that we are sort of, Norwegians learn about is that we have a very strong meteorology tradition. And one of these traditions, one of these meteorologists who were sort of like, well known for starting the school was this Wilhelm Bjerknes. It used to be it's like you were honored when you put on a tail of a Norwegian airplane. And now I don't really know anymore, but anyway, he is certainly very well known. And he said that weather prediction is a mathematical problem. And what he meant is that at around the 1900, he said that the classical laws of physics were known, well, not relativity, but that didn't matter for the weather. And he said, well, if you know we know how atoms move, we know how to describe the basic laws describing the weather at the sort of like the small level. So it's, if you could just put everything, describe all, like make a big mathematical calculation, you should be able to predict the weather. Of course, this was not possible in practice around 1900. Actually, it's actually interesting to read the history of weather prediction, because it's before it became, now it's sort of is what we call a mechanistic models. Now as I'm coming to, you can sort of compute the weather using the laws of physics. But before that was possible, they did something more like statistical weather prediction. So which is very similar to statistical modeling in neuroscience, actually, because you look at you essentially look at what is the weather now, and you measure the weather now, and then you look on what was the weather in the past, the last 10 days, and you take the average of the weather in the past, sort of like all the different weather patterns in the past leading up to this particular today's weather pattern. So it's a little bit like a spike triggered average. Anyway, that's not the main point here. Anyway, but the point is that they couldn't do this. This just illustrates that you have all these different scales which are connected all the way from like 10 meters up to I guess that's 10 to the 4 and 100,000, 10 to the 4 kilometers. That's like how much is that? That's 10,000 kilometers. So that's essentially the size scale of the Earth, that you have all these interconnected scales. And so and it wasn't possible to pursue this program until the advent of the computer. I think the first weather forecast from mathematical models came in 1954, but now all weather forecasts are computed from such models. So this is the weather forecast for Eresfjord, which I looked at a couple of days ago. I don't know how accurate it is, but at least, of course, statistically has been shown that this is by far the best, and give by far the best sort of like weather predictions compared to other methods. And interestingly, it's also a steadily improved quality, that it predicts one day better into the future per decade, meaning that the accuracy of predicting weather 5 days into the future today is like the accuracy of predicting 4 days into the future 10 years ago. So we're getting steadily better. And this is because this is like this fantastic collaboration between people doing measurements, doing modeling, all kinds of numerical tricks on supercomputers. And it's like this, clearly this international community that has developed these methods. And it's fascinating because in this day and age where people often try to make a name for themselves in science, nobody has heard about like a meteorologist. You don't have a meteorologist, Einstein, and certainly, and so it's more the community which is the hero. So this is just to make a point that it's possible to solve this, to be able to accurately predict and to bridge all these scales like they do in weather forecasting by essentially doing physics type modeling on the computer combined with a lot of statistical tricks and so on. Another example where we bridge scales is like a smartphone. So also here, I mean, you can actually make this analogy between the brain, the different levels of the brain, atom, molecule, molecular network, neuron, neural circuit brain, and the same kind of. You can also make this level, well, similar analogous levels, atom, crystal, like tailored materials, like this semiconductor heterostructures. This is what I used to work on before I got interested in neuroscience. Then you have transistor and chip and so on. So then we can ask, and if you sort of ask, no single individual in the world can make a smartphone, right? I mean, you have all these specialists at different levels. And so how were like the world was, how was the community of scientists and engineers able to make such a thing? Well, you need a very precise language to have this precise communication between people working at different levels. And that language is, of course, as I think many of you agree with, is mathematics, right? That's the only thing where the language which is so precise that you can actually do many derivations in a row and still many operations in a row. And if you could do the math correctly, then you actually get the correct result, or the result holds even after many such derivations. And actually, if you also look at to make these smartphones work, and so that you're able to say program, like I can sort of push a button and then push an icon and get out the weather in Einevoll, because that relies on programming. And there you also have, let's see, there you have also different levels. I mean, I think there's 4 levels of programs on top of each other that sort of from like down to from the app programming down to sort of like down at the transistor level, at the machine language. So what's the status for neuroscience and computational neuroscience? Well, I would say, let's see, largely we know the laws of physics or chemistry, whatever you call it, well, the laws of nature for at these different levels. I mean, we have obviously the quantum mechanics, and then you have this chemical rate equations, and at the neuron level we have this cable equation and so on, and at the higher level you can even sort of make approximations like firing rate models and so on. So we sort of have the mathematical framework. What we don't know, so the framework is ready, and so I would say that the principles of brain modeling is well established, I would say. I mean, at least it's we know how to sort of model individual units and put them into networks, and and we also know pretty well how to link this, or I would say like the first 2 here, like modeling the information flow, has been worked on for a long time, at least since the like Hodgkin and Huxley and so on in the early 50s. But the final piece here, which is this handbook of neural activity measurement, is added just to illustrate that you also need to do the measurement physics right, meaning you have to, if you have like a network model for a piece of a piece of say a piece of cortex or whatever, you need a way to link your model predictions to the things that you can actually measure, because typically what comes out of a model is action potentials, and people compute spikes, and I'm quite sure you have many lectures on how to model spikes and how to analyze spikes, but that's typically not what is certainly not the only thing that is measured. And in fact, it's other measurements that is maybe better suited for at least if you want to understand networks, at least as a key complement, because spikes are quite noisy. So there's like and it's difficult to measure many. I mean, even with the best multi-electrodes you have, it's difficult to measure more than 100, well, at least per shank, like the NeuroPixel probe that the Allen Institute is making, you can make typically measure from 80 or 100 neuron spikes at the same time. And then you can, of course, have many of those, but nevertheless, in a particular column, you can only measure like 80 neurons, which is a very, very, like, it's severely undersampled if you want to understand what in detail what this column is doing, while other measurements like the local field potential and other electrical brain signals contain more information on that. But at least it's this is sort of the good news, I would say. We know how to, I mean, we certainly don't have like we certainly don't, nobody will say that we claim that we understand how the brain works, how it computes information, but at least we know how to model the building blocks. So if you want to compare with I used to do with I worked with solid state physics before, and there we can say at the same level say that, well, if you want to understand the electrical or optical properties of a piece of metal or a piece of semiconductor, what you have to do is sort of to put a bunch of atoms with their electrons and stuff in a lattice and then compute what the electrons are doing. That's easy to say and hard to do, but at least we know sort of we have a solid starting point. Here in the brain, we know that what we have to do also, we have to put these neurons and connect them up in the network. One of the things that makes neuroscience harder is that we don't really know all the parameters, because there's so much more heterogeneity in the neurons and certainly the parameters, while in like solid states all electrons are the same. So in that sense it's simpler, but at least we know how to do sort of like physics type modeling in principle. And if we start, I think we have one thing which is also very good, that we seem to have like a quite solid starting point we know how to model neurons quite well. We know how to, this key is starting with the work of Hodgkin and Huxley. We know how to compute how single neurons receives input from other neurons and compute and generate action potentials. We know how to model in principle how these neurons with the dendritic trees and so on actually receive synaptic inputs and integrate these inputs and produce new action potentials. So this is mainly, so we have now this rather solid starting point. We know how to model neurons, and we have all this, of course, is the thing that makes neurons different and makes neuron interesting, make them able to fire action potentials, are these particular ion channels that are proteins. So that's sort of like, you can model them at like a molecular dynamics level, much more detailed, but that's not really necessary. You can sort of also make this more sort of like, well, the descriptive models and physical models. So anyways, I would say that we pretty know, if I want to tell my a relative in a Christmas party, what do we know about the brain? I would say, well, we know pretty well how single neuron operates and the principles for that. But what we don't know is sort of how networks of such neurons operate. So yeah, I just want to illustrate that we can model these single neurons. So this is just an illustration that was made in our group. I think there's like 4 neurons or something that receive synaptic inputs, not shown exactly where they are, but that's some of these dendrites. What is color coded here is the membrane potential, and you can see sometimes it fires these flashes, and that's when I fire these action potentials. So the point is that we can sort of in this sort of universe, we can sort of compute everything, and we can try out different morphologies, ion channel distributions, and see what happens. And it's also here in this animation, we see 4 dots here. This is just to illustrate 4 electrode recording points that is sort of maybe attached on this electrode, because that's something, as Ivan mentioned, that we have worked a lot on in our group, is sort of to make the link between if you have neurons which are active, like these ones, and what you would measure on these electrodes. So that's the measurement physics problem. So that's, and of course, the spikes that you pick up, for example, on these electrodes, that's one example and of an important electrical brain signal. Okay, so as I said, from going from the neuron to neural networks is much harder, and there are several reasons for that. Because it's, if you want to test your, if you want to make progress in, like, say, understanding sort of how like networks of neurons work, you need to make models, and then you can sort of make models, say, in a 1 cubic millimeter of cortex. If you want to understand a cortical network, it's 100,000 neurons, and of course, like 1 cubic millimeter isn't too much, and so. But even 100,000 neurons, if you want to model them at least with biophysically detailed neural models, that's difficult to do just from a practical point of view. So even if you have an idea about what you think an interesting model for 100,000 neurons, biophysically detailed neurons are, it's difficult to test how to. I mean, it's difficult to test out the model on a computer. And of course, if you want to explore, if you want to do science on a model, you need to be able to explore the behavior of the model in different parameter regimes. And if you have a network model with 100,000 neurons, then of course there's a bunch of parameters there, and the many parameter combination you want to explore. So it's difficult to really just analyze the model, because each run of the model takes a lot of time and requires a lot of computer power. So that's why I saw this nice quote: "It takes a world to understand the brain." I think that's sort of the, I think that was a nice quote, because in order to deal with just this always a methodological complexity of trying to understand this very complex system, there's been a lot of international initiatives taken, and there was like this large, I guess many of you have heard about the Human Brain Project. We've been involved in that, or we are involved in that, where our job is like one important Human Brain Project involves many things, but one thing is sort of be able to have these different network models, both like the biophysically detailed models, but also then models at the level of integrated, like point neurons, integrated fire type models, and also firing rate models, so at different levels of detail, and then be able to run them efficiently on computers, which are centralized somewhere in Europe, so that, for example, you can sit here in Einevoll or whatever you want in Norway, or all over Europe, or all over the world, and actually be able to run a simulation when this is ready on these centralized supercomputers in different places in Europe. So I think this is, if you think of sort of like the history of how you could do neuroscience, it used to be that in order to do neuroscience, you had to be if you want to do computational neuroscience in particular, then in order to get access to data, you needed typically to work in a lab, or be collaborating, be like an employed modeler in a lab, or at least have a close collaborator which gave you some data. And then when people started doing some data sharing, then you could sit other places like we do here. This is our group in NMBU, the lower dot here. We could sit here and get work on data recorded elsewhere. Nevertheless, we had to make the models ourselves and run the models ourselves on our own computers. And that's difficult to do if you want to run large-scale network models. But now you should be able to sit anywhere where you have a network access and be able to run not only get data to construct your model and to test for testing your model, from like this large scale or this pooled resources, you should also be able to sit anywhere and run and just log into supercomputers and run your model. So I think it's a way to really mobilize a lot more brains, so that we can do neuroscience. So I've been thinking of, if you think of sort of like the outside Europe in particular, if you think of sort of like the number of eager brains in countries like India and China and Indonesia and Nigeria, and like there's very populous countries where many people now get access to at least laptops. So now you can have all these people working maybe to make sense of all the data that is now recorded in maybe not like the western part of the world and well, some rich parts of the world. Then that's like the Human Brain Project. Then we have the MindScope project, which I think is very fascinating. It's I think you all heard about the Allen Institute for Brain Science in Seattle. This guy who started the Microsoft with Bill Gates, and well, I've done many things with his wealth, including starting this Allen Institute for Brain Science, where they have focused on like the last 10 years, really making a really detailed neurobiological study of the mouse visual cortex, both like electrophysiology, anatomy, and also sharing their data in a very efficient way. And so that's like many people just, obviously it's been for this transcription maps and all kinds of things. So it's a very, very popular site. And because it's funded by a private person, Paul Allen, who insisted that these data should get out to be made publicly available even before you'll be able to write papers on them yourself. It's been this very aggressive style of making data available. So it's sort of a little bit almost ironic or paradoxical that the most data which has been recorded based on funding from public sources are in practice often not available for other scientists, while the only data which is really available has been funded by for everyone, has been funded by a private person. So of course it's also now publicly recorded data which is now also been made public. Then you also had this brain project that was initiated by Obama. So these are all large-scale projects, and there are also other international initiatives from Australia and China and Japan, where we're trying to essentially the same idea that we have to pool resources and to deal with this complexity. So we also wrote this, I think, this perspective article that came out in 2019, and about why we need to do brain simulations, because I think there's been some I think it's many of you know about this discussion about the Blue Brain project and whatever and Human Brain project, and there was all kinds of like discussions and even like whatever petitions against like the project and so on. It was really strange, and luckily it's a very unusual thing to do, to start petitions against other people's projects. But there's also been a bit confusion about what these large brain simulations can do, because it's not like these large scale brain networks can be expected to be that you sort of just put the model together and somehow it's like a miracle the genie comes out of the bottle and it's like behaves in a way that is in any way similar to real brains. So in order to make this point, which is also as described in this paper, is we sort of compared with if you sort of look at Newton. If you go back to Newton, of course, almost the founder of modern physics, he had this idea about the movement of planets. So his physics idea was that you have this gravitational force between two masses, and this could be the moon and the earth, or the moon and the sun, or the moon and an apple, whatever. And then you have this, he assumed that it had this attraction which is proportional to the masses and inversely proportional to the distance. So that was the force, and then he needed to assume something about, well, how does a mass behave, or how does it change, how does it move when a force is acting on it? And then he came up with F equals ma. That is actually a force, means that it changes velocity, it accelerates. So this was, of course, turned out to be a good idea. But how could Newton know that this? How could he test this idea? Well, then you needed mathematics. It's not so obvious what these laws by themselves tell you about the orbits of planets, whether they should be circular or square or whatever, right? So this was sort of you needed math to look at the consequences. And so he had to check whether his idea was right. Then he ended up actually inventing calculus, because that was sort of so he had to invent sort of a new type of mathematics. Actually, historically, he did something with like geometry first, but he invented also calculus, and that's how we learn mechanics today. So without this calculus or like mathematic techniques, you wouldn't be able to check whether your theory was right or wrong. So it was only after he sort of came up, after he was able to look at the consequences, compute the consequences, that's when he sort of saw that his equations, sort of his laws, predicted the right orbits of the planets, and even predicted an unknown planet, because it was some kind of eventually, because it was some discrepancy between his theory predictions and some detailed orbits. This was like 100 years later or something, or 200 years. But anyway, so this was sort of like an extremely successful theory, which also explained like the ebb and flow kind of things with the oceans and so on. But the point is, he needed calculus to be able to compute all this. So I say, like, this large scale brain simulations is not a hypothesis by itself, it's a hypothesis tester. And so coming back to our role in the Human Brain Project is sort of to do this, to compute, to make the link between model predictions, whether it's like neurons or networks, and like model activity, dynamics, and what you would measure with different recording devices, whether you have typical electrical or magnetic recordings, if you have an electrode inside the brain, or at the cortical surface, or at the scalp, or even like EEG, or even magnetic field outside the brain, outside the head. So as I said, in order to falsify a theory, we need to be able to compare model predictions with experiments. And now there's a bunch of new experimental techniques that has been developed. I would say maybe if you look at the last 20 years, like the first 2 decades of this century, or the last 3 decades, I think the strongest development in neuroscience has been on the methods developing for measurement. I mean, obviously you have and maybe in particular, while you have the development on electrodes, that you can now measure electrical potentials at more and more positions with more and more electrodes, but also that in terms of optical techniques, where you can now not only you can put in different kinds of like molecules that makes them make it possible to measure this like activity, particularly with the calcium imaging, 2-photon calcium imaging, where you can get very high spatial resolution, and also then optically activate networks and so on. So, but then, and this, of course, and each of these techniques, of course, they tell something different about what the brain does, or what your piece of neural tissue that you cord from does. So I like to show this I think nice image. If you sort of were like in a foreign civilization, and you imaged, and it came out, and you sort of like one of these UFOs that the Pentagon will not admit exist, that actually orbit the Earth, and you can measure them well, one thing you could do, and this is actually the top one, is an imaging of electrical activity. And this is actually put together, is like just like an image put together from satellites on the, like when they're taking pictures from the night side of the well, when they fly over at night, and they put it together. So here you can sort of, just looking at this image, you could get the impression that where people live is really on the east coast of US and parts of Europe, even like southern Norway, and even Einevoll, it seems like people live, which is of course not true, as you know, you've been there, and also India, and then Japan. Of course, if you had some kind of other measurement device, so this is sort of what we measure with inverse modeling and EEG and MEG. But instead, if you're able to measure, image the hemodynamic activity, essentially food consumption, you would get a very, very different image. So there you would see that people typically live in India and China, and some points in Europe, and well, down here also on the coast of Brazil, but certainly not up in Norway. So the point is that none of these images gives like the full picture. You have to, they are complementary, but together they give you more information than each of them individually. So okay, so what is then, we take a short break, but first we'll just take this slide. And so what you're sort of advocating is that, I mean, if you want to sort of do like, I mean, the physics type modeling, the physics approach to natural sciences is that you make a model, and in terms of like a mechanistic model, in terms of the building blocks of the thing you're interested in. In our case, it's neurons. And then you hook them up. If you're sort of interested in a piece of cortex, which is the example here, there's like a piece of visual cortex where in this case, a mouse processes visual information. Then you would like, I think for I'm like a good understanding, you would like maybe both a model in terms of the biophysically detailed neurons, and Anton Arkhipov is actually going to talk about that. We are collaborating on this endeavor, and they have made this fantastic model at the Allen Institute, spearheaded by his group. So then you can have this model at the level of biophysically detailed neurons, but also you would like to have the model at the same model at the like reduced maybe to point neurons, the fire type neurons, and maybe even firing rate, population firing rate models. So the thing is that, of course, these models, if you move upwards, it gets it would say that it gets less and less it gets fewer and fewer dimensions in the mathematical sense. There are fewer and fewer differential equations. So they get low dimensional, at least lower dimensional. So you don't expect them to explain. I mean, you expect this kind of model in principle to be able to explain much more data, much more observations. Nevertheless, you also need these models in order to, just sort of to gain a better understanding of what's going on. So it's sort of just like, in some sense, it's like it's a combination of, if you look at the gas, the combination of the molecular understanding of gases and the thermodynamic understanding of gases together gives a very good understanding of gases. But the thing is, typically lots of people have been working on making models here, but they typically have been comparing with spikes. So that's typically what the model has been producing. But there are all these other measurement modalities, particularly like these are electrical. I'm going to talk about that after the break: LSP, ECOG, EEG, MEG, and also optical measurements like voltage sensitive dye imaging and so on. So what you would like to do is you sort of formulate your hypothesis in terms of mathematically specified models, and then you sort of make predictions about these measurement modalities or the things that you have measured, and then you go back and forth and try to make contact or make the model essentially predict that you measure. That's sort of like the standard physics approach. So the reason I'm interested in electrical signals, electrical brain signals, other than spikes, because well, I'm interested in that too. But that's, you can actually measure spikes, and even though you cannot, you can sort of a spike, even though we don't really maybe not understand exactly why the spike looks exactly what it does. You know that it actually, if you have a single spike, you know that it corresponds to an action potential in a neighboring, in a neuron which is closest by. So, but the reason I'm interested in doing this electrical brain signals, well, this is one of the main reasons, that you will be better able to falsify your models. So I think this is a good time to take a 10-minute break, and then we can start talking about the brain signals, electrical brain signals. And
Perfect.
so let's see. And that we're having in late September. What we call, we were towards a multi-purpose neural network model. So that's multi-purpose. We mean that you want to have models that are able to predict many things at the same time. Often in the model set there, we sort of look at network models that are maybe account for orientation, selectivity, or certain features that is observed in the firing of neurons. So in some sense, we want to sort of try to go beyond that and make sort of more, say, like large-scale network models that are able to predict many things at the same time. So for those of you who are interested in that, can just look into that. And of course, it's a free online workshop. You only need to register. So, but now I want to sort of if you sort of look at, if you sort of want to tell, I mean, if you sort of want if you want to tell what have you really found out about how networks work, right? I mean, we know quite a bit about single neurons. We can make models of how single neurons integrate information and make action potentials. But what about what is going on in real brains? And I think the main take-home message so far, the things that we really learn, is about neural representations. So if you sort of measure then, if you sort of focus on then like a piece of cortex, you have all these neurons, and then if you put a sharp electrode close to the somas of these neurons, then you can measure spikes from that particular neuron, and then you can investigate, okay, what kind of feature, what feature does sort of what does, when, under what circumstances is this neuron firing action potentials? And that's often called a receptive field of a neuron. And I think the most famous, and the one maybe like that was started this, at least in mammals, was the work of Jubel and Wiesel, where they found these cells in the visual cortex which responded only to bars. They didn't respond very much to like circular stimuli, which was sort of the which has been seen for cells in the retina and in this LGN, which is this relay station between the retina and the cortex. But back here in the cortex, they found cells that responded only to bars or things which had elongated. And not only that, they found that each cell only responded to bars oriented in a particular direction. Like, for example, in this case, the red bar orient in this direction made these action potentials, which are shown as spikes here, or these like bars here. While if you had the same, if you're just rotating away from this optimal orientation, you get less and less firing until you got none. So that was the start of this like hunting for receptive fields. This was done in the late 50s, and then we started looking for like cells coding for both like touch and movement of muscles. So you made this what's called homunculus. So that was at the like this cells at the top of the cortex. And then we even found this famous Jennifer Aniston cell, this patient. Of course, this is not something you see in mice, or maybe you do, I don't know. But at least this was a cell that was found in a patient in Los Angeles, 2005, male patient who then was waiting to undergo some kind of brain surgery. I think it was for like epilepsy, and they had like some electrodes implanted in different parts of the brain, so that neurosurgeons could sort of learn where the epileptic seizure started and plan the surgery. And then they found these cells that only responded to Jennifer Aniston. So that was like a Jennifer Aniston receptive field in some sense. That's sort of what the receptive field of that particular neuron. And of course, in Norway, the famous, our most popular receptive field is it's a grid cell receptive field, which sort of represents where in a room, like well, in this case, a rodent is. So that's been, and that's typically, so that's typically what has been done. That's typically been a way to analyze data, measuring spikes and look for receptive fields, or now maybe even more, you can sort of look for other like statistical measures. And if you measure different things at the same time, you can sort of like, there's different kinds of statistical measures. With receptive fields is essentially look for the correlation between spiking and some kind of external feature. And then so that's like the simplest statistical measure of activity. But there are many measures of cortical activity. I mean, one thing is the spikes, and if you're really good, you can also impale the cell, even in vivo, and measure the membrane potential, but that's very hard to do. The typical thing what is measured is the extracellular spike, which gives a measure of the firing of action potentials of the neurons with the somas nearby. Then you also have this, you can put in another type of electrodes. And what has been popular in the past, or in the last couple of decades, is to put in this multi-electrode. So that's electrodes which have many contacts, not only one at the tip, as like for this sharp electrode, but many recording points. And now I think with the newest electrodes, I think they're just like they were talking about many hundreds and up to thousands of these contact points on each shank, which is like a fantastic achievement, because of course all of these contacts must have individual wires going out here to the amplifiers and recording device. But with this, the point is that here you don't get like so sharp spikes typically as you do with these sharp glass electrodes. So here you typically measure spikes from many neurons, or at least a few neurons, and that is called the multi-unit activity. And that's contained in the high frequency part of the signal, maybe about like 300, 400, 500 hertz. While the low frequency part, the local field potential, then actually is harder to interpret directly, because it measures not spiking directly. It actually reflects the synaptic inputs and how they are processed in dendrites. But then you have a bunch of optical techniques where it's all based on the same thing. You typically shine in light and measure what comes out, and then you can put in different kinds of inks and materials, so that you can sort of, depending on what you put in and how you put in the light, you get different information. You have 2-photon calcium imaging. gives the information about the calcium concentration, intracellular calcium concentration, which is correlated with spiking. And then voltage-sensitive dye imaging gives information about that's ink molecules or like reporter molecules that creeps into the membrane of these cells, and the light that if you shine light on them, or particular the right kind of light, then the signal that is returned is proportional to the membrane potential, or measures the membrane potential across the membrane. So it gives like a measure of the membrane potential for, of course, not from in practice, not from an individual neuron, but more from like dendrites of a collection of neurons. And then you also have intrinsic, optical imaging, which is then that's also a measurement technique where you don't put in anything, but you also don't get too precise information out. In terms of the electrical and magnetic brain signals, which are the ones with most interest here, you can put down an electrode inside the cortex, or this is shown on a like in a cross section of a human brain. So this you never do for just research reasons. You always do it for some clinical reasons, preparing for surgery or something. So if you then put in the electrode, put an electrode down here inside the cortex, like here, you can then measure both the LFP and the spikes. Or if you have like electrodes at the cortical surface, it's called ECOG electrode, then you essentially measure activity from the same type of neurons, but it's less focused. I mean, you're further away from the sources. So at least you have many more neurons or these columns contributing to the signal. And then you can measure the potential at the scalp with EEG, and also magnetic field, MEG. And so that's essentially the type of, so when I talk about electrical brain signals, I typically mean how to model like or LFP, spikes, ECOG, and EEG. But it turns out that if you know how to compute the EEG, it's not so different, or it's not too hard to generalize it to also compute the contribution to the magnetic field that you can measure with MEG. So what you do with these measures of cortical activity? Well, traditional way has, as I said, been to look for correlations between measurements and stimulus and behavior, like you do with a receptive field. And then if you were able to measure two things at the same time, or many things at the same time, you typically what's called multimodal measurements, different measurement modalities. Then you look for correlations maybe between different experiments. So you still do this statistical thing, and I've seen it's quite difficult to actually to analyze these things and to make sense of this statistical analysis for when you do so, like, because it's not really a clear. It's not very clear, typically not very clear results and conclusions coming out from such studies, at least in my opinion. So what we are sort of pursuing is rather what we call physics type multimodal modeling. Because if you have this neuron, and which is then embedded in cortex between these layers, and you have a biophysical model of it, then the spike or the MUA, or the contribution to the multi-unit activity, really is, I mean, we say that the spike measures the action potential, and it's true that every time you have an action potential, you see a particular waveform in the spike, in the extracellular potential. But if you want to compute that waveform, you need to know the basic measurement physics, and the basic measurement physics says that it's actually a weighted sum of the transmembrane currents in the soma region. So it's the transmembrane currents that generates this potential that is measured by this extracellular electrode. And the LFP or the EEG and MEG actually correspond, well, I reflect the weighted sum of the transmembrane currents all over the neuron. And the voltage sensitive dye imaging, then it's the weighted sum of the membrane potentials close to the cortical surface. So we need to work out the mathematical connections between the neuron dynamics and different experimental modalities. But the good thing, if you do that, so what's called the measurement physics, then all of these different signals actually corresponds, can be computed from the same underlying biophysical neural model. So then you don't have to do this just do the statistical correlations, which is very much harder to interpret. So that means if you do this physics type multimodal modeling, you're able to actually use all of these recording data at the same time to constrain sort of models for neurons and networks. So the perspective for model testing is that if you have a candidate model for, say, network dynamics in the cortical area, just like shown here, it should predict all available measurement modalities, not only spikes, but also these other measurement modalities. And here we want to focus particularly on these like electric and magnetic measurement modalities. And we also need neuroinformatics tools to make this as simple as possible. So meaning that this is where everybody, well, people interested in information processing of how neural circuits or do information processing, how signal flows in the brain and what they mean and what they encodes and so on. They put up a model in terms of networks, neural networks of neurons. But then if you have that model, you need to falsify your model by comparing with the things you can measure. So then you have to make the measurement physics link. But that is not something that everybody needs to do independently. That's just something you have to do correctly. So you can just use a tool. It can be done once and for all. So our group, we have been developing this LFPy tool, which really stands for local field potential in Python, but it's somewhat of a misnomer now because it's not only LFP that you can compute, but also now the new version that came out that we finished a couple of years ago. You can compute, spikes and MUA and EEG and MEG and ECOG, all kinds of electrical and magnetic signals. So this is an example of what comes out of this type of population. So what this is a little bit difficult to see, but you see this brush here really correspond to 10,000 biophysically detailed neuron models. So it's like so that's it's called a Hay model. It's one of these like well-known biophysically detailed layer 5 pyramidal neural models. And here, these dots here represent positions where you measure these extracellular potentials. And this is not a recurrently connected network. So all this network does is really to receive synaptic inputs to these cells. And this varies over time, and that's shown on the left here. In this phase, it receives input all over the place. Here, it receives input at the bottom, and here it receives input at the top. But the average firing rate is the same input firing rate is the same always. I think this, so this sort of tells the firing of these cells. So the point is, even though in all cases, this input makes these neuron firing action potentials, but because the synaptic inputs are so differently placed, that you get very, very different extracellular potentials, very different LFPs. Like, for example, if you have all over the place, you don't get a strong LFP at all. If it's at the bottom, then you get a strong negativity. And if it's at the top, you get the opposite, a negativity up here. So this just illustrates that the LFP, even though the firing rate, resulting firing, sometimes the same, the information processing done by this silly network is the same, you get very, very different extracellular potentials. So it's not like a simple rule of thumb that you can just look at the LFP and say, well, this network gets inhibition here or excitation there or whatever. So you have to, in order to analyze it, you have to build mathematical models and make predictions. And this is the same thing in terms of where you compute the EEG that would be measured if you had this population at the inside the brain here. And this is just illustrating populations. And on the way to this EEG electrode, it has to pass through this like the skull, which is insulating, a scalp, which is the skin, which is sort of quite conducting, CSF, which is this fluid, which is high conducting. And this is sort of what you would measure with EEG electrodes placed on top of the skull in this particular spherical head. So we see during one phase you get the negativity, or is it a positivity? I don't really. It's a positivity, and then you get the negativity, and so on. And the same thing, and you get a quite different signal if the population, instead of being vertical, is horizontal. Then you get a very different. Then you get a quite different pattern. And here is the same thing we see for MEG. So this is the magnetic field, and so the point is this is like a very, very slow network, but even for more complicated networks, these forward modeling tools apply. So now if you have a network, you can compute spikes, LFPs, and EEG and MEG, and so on. So this is something which we just finalized, and then you can, if you're interested, there is this paper out that came out that's just earlier this year. So now we're going to focus on after hopefully motivating why this mesh modeling of these electrical potentials are important. I'm going to sort of talk about the signals in more detail, and or where they come from, because this electrical potential is sort of among the oldest and conceptually simplest measurements of neural activity. It's been measured since 1875, but at that time it was like just because the equipment, the electrical equipment, wasn't so good. It was like limited resolution, but the principles of all these measurements are the same. So you have this, in this case, a recording electrode, which measure the potential difference between the tip here and a reference electrode far away. And then you will measure just the signal, which is a potential difference, because electrical potentials are always measure the difference between two electrodes. So typically this reference electrode should be far away so that it's not affected by brain activity, so that it's sort of like more like it work as like effectively like a ground electrode. Now, one thing about this potential is that it's like the typical membrane potential is like 60-70 millivolts, like almost like 1/10 of a volt. This is much smaller. This is typically less than a millivolt. So it's a much smaller signal. Of course, a millivolt is still a quite big signal given today's amplifiers and so on. But nevertheless, it's not difficult to measure. But nevertheless, that should be kept in mind. And the typical analysis, if you do these extracellular recordings inside the brains, has been to split the signal into two frequency bands. First, the high frequency band, multi-unit activity, which then measures spikes in neurons surrounding electron tip, or the low frequency band, LFP, which measures sub-threshold activity. So that's typically been filtered, and so historically, even though the LFP, local field potential, has most of the power of the signal, it was thrown away. I think for one, because it was much harder to interpret. You couldn't just hear with each spike. You could say, well, that corresponds to an actual potentials from a neuron. But LFP corresponds to some kind of collective behavior, but it's much more difficult to make rules of thumbs and explain explain it in terms of just like neurons with like make this simple explanations. So also it was this, as it contained, it also just lack of hard disks to store signals made it so that many labs just threw this filtered out the signal and just kept the spikes. So it was often discarded. It was sometimes used in something called CST analysis if you had laminar, like electrodes spanning cortical layers or hippocampal layers. But there's been a revival in the last decades. One, because you have now more and more, they have large hard disks, more and more large hard disks, cheap hard disks, so you can store the signal. But it's also been realized that it's like unique window into activity in populations of neurons, because it's difficult to understand what groups of neurons are doing just by measuring spikes. And then it's like a candidate signal for brain-computer interfaces, because it's more stable than spikes. And we got interested in it because back in 15, 20 years ago, where I was collaborating in the lab of Anna DeVore and also Anders Dale and István Ulbert had these really cool electrodes where they had this. Anna did these recordings where she put this multi-electrode inside the barrel cortex of rodents. And the barrel cortex is this fascinating thing that encodes information about like whisking activity or whisking, sensing with whiskers. Like rodents has about 30 whiskers on each side of the snout, and each of them has a particular place in cortex. And if you put in an electrode, multi-electrode through one of these columns, these particular places, and flick the right whisker, you get a strong signal. If you flick the neighboring whisker, then you don't get a very strong signal, and maybe not signal at all. But this is what the signal looked like. If you had like the stimulus onset here at time 0, and this is like the 22 different recording contacts from the top of the cortex to the bottom of the cortex. So the distance is 1/10 of a millimeter between these contacts. Then we got this volley of activity starting about 10-15 milliseconds after you flick the whisker. And if you do the high-pass filter, you got the multi-unit activity, and you got a quite different signal. So the idea sort of was that, we know that this probably reflects spikes from neurons in the vicinity of these different contacts, while this measures sort of like the dendritic processing of the synaptic input. It's not so easy to just look at the data and come up with conclusions. So then we started looking at sort of maybe we can make models for it and compare predictions directly. And then, because one really good thing is that the physical origin of LFP, it's in spikes, and for that matter, EEG and MEG also, is the same. It's transmembrane currents. So the thing is, if we have this very schematic setup, if you have one piece of cortex and say that there's only one neuron in this piece of cortex that is active, meaning having transmembrane currents, that's this orange thing. And then if we have a excitatory synapse injecting current here at this, giving a like synaptic input at this red synapse, there will be actually current going in to the synapse here, and then into the neuron here. And if you for now assume that what we call a 2-compartment neuron, so that all net current that goes in here must leave here, then from the point of view of the extracellular electrode, then you have a current sink here. Current vanishes, and the same current has to leave out here. That follows from essentially the cable properties of the neuron. So you have a current source, and the same current comes out there. Current sink here, and the same current comes out here as a current source. So then, if you know the distance between the sink and electrode tip and the source and electrode tip, we can compute the extracellular potential. Oops. So this is what's called a forward solution. So then the total potential is sum actually of two terms. One term from this from the sink given here, and one term from the source. So it's a very simple expression. it's the potential is simply given by the current that goes in here, divided by the radius in the 4 pi, and this material parameter called sigma, called extracellular conductivity. And then you have a similar term from the source here, similar contribution from the source. And it's sort of a warning here is that it sort of looks like Coulomb's law from those of you who have studied electrostatics, that the potential is given by like the charge divided by 4 pi and then the dielectric constant over R. But that has the same mathematical form, but the physics is different. Here, this is the potential from a current in a conductor. So this is, because this neural tissue should be thought of as a conductor, just like a metal, except that the conductivity is smaller. While this Coulomb's law actually applies for in vacuum or in a dielectric. So that's it's just like a very different material. But the point is, this is a very simple model, simple formula, and one immediate observation is that current monopoles do not exist, meaning that if you are since the current gas goes in here must come out here. It's like it follows actually that well, some sense if you only or you can think of it if this neuron shrinks so that the sinks and source end up at the same place, then you will have a net zero current. So then you have not an extracellular potential at all. So the simplest neural model that sets up a potential is a dipole like the one shown here. The current monopoles do not exist. Current dipoles is sort of like this dominant term typically, but you can also have like higher order poles and multipoles and so on. So anyways, from far away, it always looks like a current dipole. And this is what the LFP from a 2-compartment neuron looks like. So here it's just like plotting this formula. Here, this is a really boring neuron. It doesn't have action potential, active conductances in the soma, so it doesn't produce an action potential. So this is just what's called a 2-compartment model, where the current goes in here and it leaves here. This orange thing is just to illustrate how it can sort of mimic a neuron, but really it's just a current going in here and leaving here. And from that it follows. From there, it follows that a current, like if you have a net transmembrane current, like a sink here, you will get the negativity. This is just plotting this formula. In close to this electrode, you get a negative potential, while far down here you get because then this term dominates, and close to the soma here you get the opposite, because then this term dominates, because then down here R2 is smallest, up here R1 is smallest. So this is the simplest possible LFP pattern. So what this means is that if you measure the potential here, have an electrode here, then you will get this dip. And if you measure it here, you will get this peak. So one thing you immediately see is that it's like just illustrated here is that it's not very local, meaning that the synaptic input up here doesn't only give rise to extracellular potentials around where the synapse is, it also gives signals down at the other end. So So what happens in this simple model is if you have like the synaptic input current shown with dashed lines here going in here, at the same time, you will have a lot of current just leaving in the same compartment. That's this positive thing here, because that will be a source. But there will be some current that goes down here, and that's this sort of like this net current. So that will only a small part will actually be so it'll be a net current going in here, and not the same net current going out here. which gives rise to this potential distribution. So what are the assumptions underlying this formula? Well, there's one is that there's a quasi-static approximations to Maxwell's equations, meaning that the frequencies, even though we say high frequencies gives the MUA, it's still only a few hundred hertz, up to 1 kilohertz, which is very slow, not very fast in terms of coupling electric and magnetic fields, for those of you who have studied physics. So you can do this electrostatics and magnetostatic approximations. So if you do this, just take the Maxwell's equation and neglect this time derivative of the magnetic field. We get this equation, which means that there's this rotation free, meaning that you can actually write this electric field in the extracellular space as a gradient of this potential, the extracellular potential. And then the second assumption is that you can describe, and that's maybe the most surprising assumption, that you can describe the propagation of signals from like transmembrane currents here to this electrode here, just even though the current has to meander between all these neurons and so on, it's quite effectively described just by this one material parameter sigma. So this is maybe not obvious why this should be so simple, but this has been tested out experimentally, that by sending in currents between two electrodes, they can be sort of very well described just by a single parameter. And then there's some other assumptions that they have a linear extracellular medium, meaning that the current, if you impose extracellular field in this medium, you get the current density in this extracellular medium proportional to the electric field, and that is like ohmic, and that this is really what it means to be ohmic, homogeneous, frequency independent, and isotropic, meaning that it's equally easy to go in all directions. And if you add actually all of these things together, these consequences of this assumption is just that it actually follows from the math that the potential around the point current source has this simple formula. So I think, and if you then have a source and sink pair, then it just gets two contributions. Because the thing is that even though the neurons themselves, of the signal processing in neurons is very much non-linear and like generation of spikes and so on, the measurement physics is linear. So the link between going from transmembrane currents to the extracellular potentials or potentials to MEG, EEG, and so on is linear. So that contributions from different transmembrane currents or different neurons just add up linearly. So I think maybe this is a good place to stop, and then I maybe then continue this tomorrow. I think we meet again at 2 o'clock, and then I'll finalize this, and then of course give some more examples where we apply this to different things.
Thank you very much, Gaute. Do we have some questions? So you were saying that the medium can be just approximated as a homogeneous isotropic conductive. So how good is that approximation? Or
yeah, so there's like several things. So like it turns out that I'm coming to that tomorrow, but about this approximation. So inside cortex, the homogeneity assumption is quite good, meaning that it's not very different connectivity in the different layers of cortex. There's some, but it doesn't really affect the propagation of electrical potentials. There's then the question is, but outside the cortex, if you sort of have like at the interface between cortex and the white matter is fattier, so it has a lower conductivity. So there you get these jumps in extracellular conductivity, which affects the potential that you measure and the propagation of signal, but it typically only affects like electrodes or signals recorded very close to the interface. And then you have this anisotropy, and that's sort of maybe up to like a 50% effect in cortex. It's easier to move in the vertical direction along this apical, like this dendrites, like depth direction, than across them. So the connectivity is a little bit higher. So, but these are things you can sort of actually modify. You can modify the formulas to take that into account. So I'm going to show that tomorrow.
So Gaute, one question is if you want to check the forward models, we have to do real measures in the in vivo environment and with very invasive methods. And does this actually perturb the other measurements? For example, if we measure membrane potential, does this perturb the LFP that is measured around it? And is there a way to check the forward model without perturbing the measure?
I'm not quite sure if I understood the question. So you're saying that if you
if I want to check the forward model, so I put the membrane potential device measurement device and the normal electrode to measure LFP. And does the fact of doing this perturb the measure of the LFP? And so
okay. So I think it's actually I think this kind of measurements was done. It's hard to do, but it has been done by it was done in Judy Bushalki's lab for a hippocampal neuron, where they had they measured the membrane potential and with the intercell electrode and the extracellular spike at the same time. So I think it's true that there's when you have electrodes in there, it sort of disturbs the situation. I'm not quite sure how strong the effects are, though. I think it certainly perturbs it, but I don't think it ruins the validation by itself. At least I think it's also in particular the LFP. It's also a question whether you validate the spikes versus the LFP. LFP typically varies less with space, because it's more low frequency. So that's probably less perturbed less affected by perturbations. But I think that if you talk about validation of this whole scheme, I think it's like they're like separate lines of validation. And I think one line of validation is actually one starting point is the cable equation. Does the cable equation or this biophysically detailed models like Hodgkin-Huxley style, is it accurate in the sense that it predicts the right transmembrane currents? So that's like one. And of course, I think it's difficult. At least I cannot understand how you could sort of get the successes of Hodgkin and Huxley if you were completely off with the transmembrane currents, because the transmembrane currents really they're at the heart also of that model. And then the second question, well, given that you have the transmembrane currents, how do we know that it computes the right extracellular potential? And that can be done separately if you're having small electrodes and injecting currents and measure the potential that's set up just by extracellular current sources. And that has been validated quite accurately, at least on a bit longer, down to 100 micrometer length scales. I'm quite sure if that was an answer to your question, but
yeah, exactly. That's.
So also I wondered with the forward modeling approach, when you simulated some cells and then you try to look at those signals, how it would look at the LFP and so on. This is only being done when they're not connected, as far as I understood. Mm-hmm. So what would happen if you started to connect them and make a recurrent network and also try to forward model them?
But I don't think so. The thing that it's recurrently connected, doesn't change the forward modeling thing. So because if when you drive it, I mean, in the example I showed with this bush of neurons, then all synapses came from the outside. So of course, if you have and so the network activity, the spiking activity is quite simplified and uniform and boring. So if you hook them up recurrently, then the spiking dynamics gets much more interesting, of course, and it's much harder to predict what kind of spiking dynamics you'll have. But the link between the spiking dynamics, or the link between the transmembrane currents and what you measure, is the same. So it's like the dynamics that makes a complicated. So the measurement physics is not affected by a more complicated recurrent network.
Yeah, I just wondered how, for example, how does the LFP signal look in that case? Because it was already difficult to decipher what was the original spike.
Yeah. So.
It's even more connected. It's even harder.
Yeah. No. So I mean, yeah. So it really depends on. We have done some. I mean, it really depends on the network activity. We've done some. I mean, like maybe I could show that tomorrow. Just some examples. We just computed the LFPs from this Brunel network model in different regimes, where you have this asynchronous irregular state and like the different kind of network like brain states essentially, and you get very different LFPs. And just like as you get very different spiking patterns, you also get very different LFPs. But then an additional complication when you compute LFPs, that it's not only the spiking dynamics that determines LFP, but it's also where on the neuron the synapses are placed, because that doesn't really matter when it comes to, well, you can think of it, at least if you have multi-compartmental neurons, if you move the synapse, but say scale the synaptic weight so that like the same amount of current goes into the soma, the spiking dynamics would not be much changed, but that could completely change LFP, and because it's yeah.
Yeah.
So, but I think in general, what you have to do, like I always say, is that, I mean, our group over the last 10 years have done a lot of like computing LFPs and spikes and so on for different setups, and often our intuition is wrong, I must say, about what you don't get what they expect maybe. But the good thing is that you can always compute it. The forward modeling scheme, I would say, is much more reliable than our intuition. You see what I'm saying? So I think the forward modeling scheme is quite reliable. I sort of think that is quite on quite solid footing.
Okay, thank you, Gaute. I think there are no more questions for now, so we can continue tomorrow at 2 then.
Yeah.
Yeah, we'll see you then. Thank you very much.
Perfect. Okay. Ha det bra.